Thank you very much, Dougal, and I think a lot of people are going to be saying thank you today, and I'm going to say thank you as well, both to the RSAA and also to my supervisor, Dr. Roland Crocker, for the opportunity to come here and work on this project. So what have I been working on? My project is related to a 40-year problem for high-energy astrophysics, quite a long-standing problem. We observe a lot of positrons annihilating in the Galactic Centre, and we don't really know where they come from. So hopefully today I'll be able to start elaborating on a possible solution to this problem. I just want to start off by saying that my relationship with positrons started about 10 years ago. I was sitting in my first ever high school physics class, and my teacher I sat up front, my eyesight is terrible, and he had this poster on the front of his desk, and it was kind of caught my eye. I was bored, I was reading this poster, and it was all about Paul Dirac discovering antimatter, and it was all about positrons and positron annihilation. So when a positron crashes into an electron, as you may be aware, it produces gamma rays, and these gamma rays have a characteristic energy of 511 kiloelectron volts. And this is a signal we see coming from the very center of our galaxy. We see it in the disk as well, but we see much more of this signal coming from the center of our galaxy. And nobody really knows why. So it's a 40-year problem for high-energy astrophysics. These gamma rays were first observed by balloon observations, and more recently by satellites such as Intern, which is run by the European Space Agency. And they've observed this signal here. So 511 kiloelectron volts emission from the Galactic Centre caused by the annihilation of positrons. There's 1.4 times as many gamma rays coming from the bulge of our galaxy as the disk, which suggests that there's something interesting about the bulge of our galaxy and the source of these positrons compared to the disk of our galaxy. And in fact, every single second, 10 to the power 43 positrons are annihilating in our galactic center. So that's a pretty massive number. And because we don't want to assume that this is some crazy coincidence, we have to say that this is a steady state kind of scenario. There's this many positrons being created every single second in order to produce the signal. So where are these things coming from? So why has no one been able to come up with a consistent description for why this is happening? Let's talk a bit about the spectrum. So 97% of the annihilation is coming from something called positronium. So you know your regular hydrogen atom, it's got a proton in the middle and it's being orbited by an electron. Positronium is quite similar, except instead of a proton, you've got a positron, and its antimatter counterpart, the electron. So we're obviously more familiar with electrons than we are with positrons, but they're basically the same thing, give or take that electric charge. And it has this lovely characteristic spectrum. So you have this sort of inward spiral of doom before the electron and positron come into contact with one another and annihilate, producing this gamma ray here. So you get kind of this lower energy continuum with gamma rays, and then you get a couple of gamma rays out at 511 kiloelectron volts, which is characteristic of the annihilation. Now, when we look at the very center of the galaxy, we see a lot of gamma rays, meaning at all energies, right from some coming from very high energy giga-electron volts, so billions of electron volts, right down to these very low energy ones, these 511 ones. But what we can say is that these positrons are being pumped out into the interstellar medium at fairly low energy, so non-relativistically. And this is really, really important in telling us where they might come from. So this is a particular fit that was done to show this. So you can see this is this positronium annihilation spectrum I was just showing. Obviously imposed on a bit more, the data points show different observations from different groups who've done observations. And each of these fits here, people put in fits of spectra where the injection energy was, I think that one's around about 100 MeV, 50 MeV, 5 MeV, and this one at the bottom, this is a really good fit here, that's down at 3 MeV. And this is telling us that these positrons are being injected non-relativistically, so fairly low energy, and they're all annihilating in terms of this positronium continuum. So what do we know so far? There's a lot of them annihilating the galactic center every single second. which means there's a lot of positrons being produced in the galactic center every single second. We know a bit about the morphology, so what this annihilation signal looks like. So there were 1.4 times as many positrons annihilating in the bulge of our galaxy, which is, this area here, which is quite dusty in this picture in the visible spectrum, but if you're looking at gamma rays, this is where you see this big, bright 511 signal. There are 1.4 times as many in the galactic bulge as there are in the disk, and also the spectroscopy, so we know that they're being injected at very low energy. So where could they be coming from? There's actually quite a lot of stuff out there, and this is where I kind of got this title for my talk, Strange Origins. And some of them are quite strange. Cosmic rays, not very strange, really. Microquasars, that's a weird one. Luminous massive X-ray binaries, it's a bit of a mouthful. Then you have compact objects, so pulsars, millisecond pulsars, and magnetars. The central black hole. So the very center of our galaxy, there's a supermassive black hole around about 4 billion solar masses. So could the positrons be coming out of there somehow? This is where it gets weird. Dark matter. So everyone knows what dark matter is. Yeah, there's a lot of silence there. It's the right answer. We don't know what dark matter is. But people have actually tried to use this spectrum to try and constrain the mass of dark matter. Whether it's successful or not, I don't particularly think so. Different things dark matter can do, various theories about how it behaves. It doesn't just sit there necessarily. And then what might seem slightly less strange origins of positrons. So massive stars, we're fairly familiar with stars. I mean, we look up at the night sky, that's what we see. We don't see gamma rays, we see stars. So massive stars, supernovas, so the ends of the lives of massive stars, and they produce various radioactive elements, including titanium-44. Supernova 1A, they produce nickel-56. So do core collapse supernova, they also produce quite a lot of nickel-56. And these quite strange things here, hypernova and parent stability supernova, which you may not have heard about before, basically they're just really, really big supernova, and they also produce nickel-56. There's a few of these we can just completely rule out from the get-go. Cosmic rays, too higher energy. We don't know very much about the jets coming from microquasars, which means we can rule them out, along with the high injection energy you get from pulsars, millisecond pulsars, magnetars. Luminous massive X-ray binaries, the kind of signal we see doesn't fit what we know about them, so we rule them out as well. The other thing that I will say about the morphology of the signal is that it indicates that positrons are they're not coming from a point source. So the source of the positrons is distributed across the bulge the same way as the signal is distributed across the bulge. And this means we can rule out a point source like the central massive black hole. Dark matter we rule out because of the type constraints it puts on the mass. So for dark matter annihilation to produce this signal, we need light scalar dark matter, and it needs to have a very particular profile. We can also rule out decay for the same reason, and de-excitation is ruled out, I think, for all profiles. So massive stars produce aluminum-26, and this produces gamma rays at a much higher energy than we see from the positrons. And we also see the signal in the bulge, in the disk as well as the bulge. So we see this aluminum-26 signal all the way across the galactic plane. And it doesn't fit the morphology. So these positrons aren't coming necessarily straight from the lives of these massive stars. Getting rid of titanium-44. Titanium-44, there's not very much that's synthesized in massive stars compared to the core collapse supernova and the hypernova and the nickel-56. And also, I'm going to take away supernova 1A for now, although this is still a possibility we are going to explore in the future, that these may be responsible for producing the nickel-56, which decays into positrons. Which leaves us with these two. So these are both really good producers of nickel-56. Nickel-56 decays, producing positrons. Okay. So this is kind of what we've come up with here. That positrons are coming from this nuclear synthesis in the core collapse of very massive stars. But in order to explain the morphology, so there's the fact there's more positrons coming from the galactic bulge than the galactic disk, there has to be something quite unique about these stars in the very center of our galaxy. And this is kind of one of the avenues we looked at, is these massive star clusters. Before I start talking too much about stars, I just need to say that for about the past year, to me, stars are point masses that you pushed around using Fortran or Python in an n-body simulation. So if I do say something wrong, I will happily stand corrected. So massive star clusters in the very center of our galaxy. These two clusters are quite famous. They're also quite pretty. I think that's why they're famous. The Arches cluster and the Quintuplet cluster. They're around about 5 million years old, and they're around about 40,000 solar masses each. So they're very dense, they're very heavy, and they're quite young as well. They contain a lot of massive stars. The most famous one is probably in the Quintuplet, which is called a pistol star. That's thought to be a luminous blue variable. They've got a lot of Wolf-Rayet stars. Wolf-Rayet stars are massive stars which have kind of puffed off their outer shell of hydrogen and helium in an expanding envelope, leaving quite a small core behind. What we're interested in is what happens at the very center of these clusters. So provided that the most massive stars can sink to the center of these clusters in a time sort of less than the lifetime of a massive star, stars might actually start to merge at the very center of these clusters. The gravitational forces are sufficient for them actually to begin to merge. And this is one way you can produce supercanonical stars. So a supercanonical star is one which cannot form via accretion. So it has to form pretty much through this merger process. You can get stars, we believe, up to around about 300 solar masses through this process. There's a bit of evidence for these things existing. 30 Doradus in the Large Magellanic Cloud does contain stars which are around about 150 solar masses, apparently. So they do exist, and what we're really interested in is how they end their lives. So, obviously, mergers. They end their lives as hypernova or parent stability supernova. So this one here is an example of a hypernova in a distant galaxy, supernova 1998 BW. The collapsar-type hypernova, so that's basically, it gets to the end of its life and it collapses in on itself. Collapsar-type hypernova produce about half a solar mass of nickel, which corresponds to quite a few positrons coming from that. Whether or not they can all escape from that environment is another question, and one which really needs a bit more detailed modeling. The other option is this parent stability supernova idea. I think Melanie and I are going to talk a little bit about the very low metallicity stars, and parent stability supernova kind of believe they originate from these quite low metallicity stars because you can form a very massive star due to low metallicity. You can also perhaps get a parent stability supernova if you have sufficient merger activity going on. So a sufficiently massive star, all that really happens is it blows itself to pieces. No remnant is left, and they can synthesize up to about 60 solar masses of nickel-56. And that's going to contribute quite a few positrons into the interstellar medium. So this idea of these supercanonical stars producing nickel-56, which then converts into positrons, seems like quite a good idea, really. You can only get these massive clusters in the very center of galaxies, so it kind of fits the morphology. The observed rate compared to the rates we've also calculated seems to fit quite well if it's a little bit marginal. Obviously more work needs to be done. But the observed external rates of these hypernovas, so about 1 in 60 to 1 in 600 of all supernova, all core collapse supernovae, will become these hypernova-type explosions. That rate kind of pretty much works with the observed positron annihilation rate we're seeing. So what about the smaller stuff? So what about these small core collapse supernovae? So the supernova type 1c. I say small. I think a lot of people doing stellar astrophysics would disagree with me that they're small. They're still around about 10 to 25 solar masses. So at the end of their lives, the very core of these stars will collapse, and when that happens, lots and lots of material will get jetted out in an expanding shell. So this is a 3D hydrodynamic simulation they did at Caltech. One of the things which gets spat out is nickel-56. Obviously, because it's a smaller star, it can produce less nickel-56 than a big star, which means less positrons. However, there's a lot more of these things. There's also some really good evidence that these things might be more common in the very center of galaxies, which has come out in the last few years. So in the Galactic Centre, the very center, you see a lot of 1C supernova, whereas in the disk you don't see very many at all. And we're not really too sure why this might happen. There's a few sort of explanations. One of them is there's a higher metallicity in the Galactic Centre, which contributes to these massive stars which have no hydrogen and helium in their spectra. There's also the idea that there may be more binary stars in the center of the galaxy than there are in the disk of the galaxy. Binary stars thought to be progenitors of these type 1C supernova. Yeah, and Yeah, that's probably pretty about it. But, yeah, so quick summary, because I think I'm running out of time here. I'm not too sure. So this is a 40-year unsolved problem, but it's one that we think we can have a pretty good stab at. There's been a lot of solutions postulated. I think if you go and look at the literature on this, there's quite a lot out there, including some really exotic physics, and that's this dark matter stuff that I'm talking about. There's some quite interesting papers out there. So the actual source of these might be a little bit more ordinary than we think, so we might not have to stretch too far to find a source of these positrons. The Galactic Centre appears to have a really unique impact on the lives of massive stars, and I think it's going to be a bit more research into exactly why that is, how that happens, and why do we actually see more 1C supernova in the very centre of these galaxies, in the very centre of galaxies than the disk of the galaxy. So what's really next from this project? What does this contribute? Well, definitely a better understanding of stellar evolution. There's a lot we don't understand about stellar evolution. A better understanding of how massive star clusters behave. And in particular, our Galactic Centre. You're going to hear a bit more about the Galactic Centre, I think, from Josh later on. And it's really a very interesting subject. So from there, I'd just like to thank everyone once again, particularly Roland for all his help and the opportunity. And if you want to get in touch with me, I'll be back in Auckland for a little while. I have an email, or if you're not feeling particularly good, Boris, you can also get in touch with me via Twitter. Thank you very much.
Questions?
Oh, do you want me to hang around?
Try
to escape. It doesn't work.
I think it's probably a couple.
Okay.
So. Garen?
Do you know whether the satellite sensitivity is such that you can see whether you get the 511 electrograph signal from, say, the bulge of M31?
The bulge of M31, yeah, that's an interesting question, actually. And also tied in with that is whether you get a similar signal from somewhere like 30 Gerardus, which is forming these massive stars. I don't think it is quite that sensitive, is it, Roland? Yeah, sadly not. Otherwise, that would be a fantastic diagnostic tool to kind of find out about what's going on.
Mike, I guess my question is sort of related to that, related to the beam size of these instruments. Can you say anything about the structure of the profiles with the Galactic Centre? Does it look consistent with the point source, or does it look like they're distributed?
It's definitely distributed, so it's definitely not consistent with the central black hole being the source or particular point sources. So it is distributed across the whole bulge. I think it's relatively uniform as well, isn't it?
No, it does peak towards the center.
Yeah. But it's not coming from a single point source. It's not consistent with the properties of the interstellar medium of the region.
I guess this might not be sensitive enough, but can you tell whether the shape of it is tracing the vertical bulge or the bar region instead?
I think it's coming from the more spherical region in the very center as opposed to the bulge. But
I think you can really tell it's consistent with the bulge the size that you. I mean, it's quite a certain you have to track up the disk and everything as well.
Okay. Any further questions? If not, then we'll move on. Thank you, Fiona.